Hi, today we are going to learn how to segment melanoma, how to detect melanoma, but it will be based on the Res-UNet architecture, as you can see it on the right side. Basically, we are going to take images of melanoma and its corresponding mask, and we are creating a model based on the Res-UNet in order to detect it on a new and fresh images. First of all, you are most welcome to subscribe my channel and discover more TensorFlow tutorials. The first phase of this tutorial, which is download the data and prepare it for the model, was done on my previous tutorial. You can find it here. I will leave a link. So I'm going to jump directly to the first phase, which is explaining what is the Res-UNet architecture. Okay, so now we have the data that is prepared for building our Res-UNet model. And before continue building our model, let's explain some more about the Res-UNet model. So here you can see the architecture of the Res-UNet model. As you probably figure out, it's a combination of, it's like an hybrid of two types of architecture. The one is the UNet model, which is shaped of U, and the next one is the Res-UNet architecture, which is basically built of components that has like a shortcut or bypass inside those blocks. But first of all, let's explain some more. Res-UNet is a deep learning architecture that is good for semantic segmentation, and it combines features of the UNet architecture, and a residual network. It was first proposed on 2017, and it showed a very good results on semantic segmentation tasks. The Res-UNet inherits the encoder-decoder architecture of the units, who have one side which is the decoder and the other side which is the encoder, and of course there is the bridge. This is the UNet architecture, and of course it consists of two main components. The encoder, the main purpose of this one is to extract high-level features from this input image, and the decoder does an upsampling of those features and generate the segmentation mask. However, the Res-UNet replaced the standard convolution layers in the encoder and decoder with residual blocks. Res-UNet replaced the standard convolutional layer in the encoder and decoder with residual blocks. This is the UNet architecture, and the Res-UNet replace those blocks. If I come back to our image, this is the areas that are being changed. The residual blocks are types. It's a type of a neural network layer that allows the network to learn more complex function by adding a shortcut connection between the input and the output of the layer. This is the shortcut, this line. This shortcut connections helps to prevent a gradient from vanishing, which can help us to solve problems for deep learning neural networks. The combination of the UNet architecture with the residual blocks make the Res-UNet a powerful tool for a semantic segmentation. Let's speak about the encoder. Okay, this left side. The encoder consists of series of residual blocks, which consist two convolutional layers, as you can see, two convolutional layers, followed by a batch normalization, this one, and a ReLU activation. Okay. These residual blocks are stacked together to form a deep neural network that extracts the high-level features from the input image. The decoder on the right side consists of series of upsampling layers, each of which is followed by a convolutional layer and a batch normalization. Okay, as you can see, this is one block and this is another block. This PN is a batch normalization, and this is the reload and another convolution. This is the structure of the decoder. And basically these upsampling layers used to gradually increase back the size of the feature maps, while the convolution layers are used to refine the features and generate the segmentation mask. We also have skip connections like this one. These skip connections are used to connect the encoder and the decoder layers, and it helps to preserve the spatial information in the image to improve the accuracy of the segmentation mask. So let's start with the first coding part, which is creating and building our model. As you can see, these are the 4 NumPy arrays. So if you already done the first part as I explained it on my previous tutorial, so you can jump directly with the second part, which is building the Res-UNet model. So first of all, we will import the necessary layers and modules from TensorFlow and define the utility functions for batch normalization and residual block. Basically, it's a straightforward. We are importing the relevant layers. We also, since we are creating and configuring our model, we will load the relevant layers and also load the model object. And the next phase will be creating some functions that will be part of our model. Okay, let's start with our new function. We will call it batch norm underscore relu. And this is a function that applies batch normalization and the relu activation function to the import. Since we need a reuse of this process, we are creating this function. The same for the next one. We will call it residual block. This function defines the residual block with 2 convolutional layers. It takes an input, apply a batch normalization, 2 convolutional layers, and a shortcut connection to handle the different spatial resolution. Same as I explained it on the architecture diagram, we are now creating each block. And since we need a reuse of these blocks, we are creating like a envelope function so we can reuse it with the different inputs, different strides, and different number of filters. Please notice that in the end of each of the commands, we are adding the X. So basically we are building like a stack of layers, and in each time we are adding another layer. So as you can see, for example, in the first block, we are adding each layer one next to each other. The next step is creating the shortcut, but please notice the shortcut will not be based on the X, which is a stack of layers, but since the shortcut is coming from the entrance of the block, it will be based on the inputs. So as you can see, we are creating a variable named S, which indicates the shortcut, and in the end we are creating a new stack of layers, and that the first one is inputs. And next we are adding this S to the stack of a previous layer named X. So X now contains all the layers of X and the shortcut as well, and we are returning this X. And now this is the decoder block, and decoder block is the right side of the Res-UNet architecture. As you can see, in the decoder block we are running an upsampling function, a concatenate, and the previous residual block. And this process, this 3 steps process, will basically help us to apply or refine our feature and then create the target mask. The last function is the most important one. We name it build Res-UNet, and this function is the core of this section. It constructs the Res-UNet model, including the encoder and the decoder blocks, and then add another final classification layer. It begins with defining the model input layer. Basically, we will use 128 by 128. This would be we will reduce the images to this dimension. Then we are starting in the encoder section. It starts with the first block that includes the convolutional layer with batch normalization and ReLU activation. Please notice that the amount of neurons or amount of filters in the first block is 64. So it's important, since on the second block and the third block it will be, let's say, a similar but different pattern, but the number of filters will be different. So as you can see, the encoder 1 contains those layers, and we had another layer named S, which this layer is our shortcut. You can see it's a shortcut since in the last command we are adding inputs. That means that it's like a different stack of layers. Let's go back to the architecture and see the next phase. So we now dealt with the first block. Let's go to the second and the third block. Basically, those section has a similar pattern. As you can see, there are a very similar stack of layers. The main difference between block 2 and block 3 is the number of filters and the reduced spatial dimensions. So as you can see, we are creating S2 and S3. Each one has a different number of filters. Both has strides 2. So basically they are the same. As you can see, we are reusing our block, our residual blocks, both in S2 and S3. The next section is the bridge section. It's represented by residual blocks that connects the encoder and the decoder, which is very similar to the concept of the unit architecture. And now we are creating the decoder part. The decoder section consists of 3 decoder blocks. One we call it D1, the second one D2, and the third one D3. Please notice the difference of the number of filters. And at last, this is the classification part. In this section, we produce the predicted mask, and since it's a binary classification, we are using the Sigmund activation function. And I think we done. of course, we have to create the model. Sorry, we need to create the model and return it from our function. So finally, we are ready to create our customized model. That means we are going to load the data and build our model and train it. So that will be our next phase. So now we are ready to customize our model and train it. So let's create a new Python file. We call it step number 3, train the model. Okay, let's start. We will import NumPy. It's relevant for loading the data. The first phase, we are going to load our saved data, the one that we save in step number 1. So we are going to load the training data and the validation data as well. And this data, I just remind you, this data includes the melanoma images and their corresponding mask. So let's wait for writing this code and load data. We will print the shape of those NumPy just to double check that it was loaded correctly. Okay, let's run it. As you can see, we have 4 NumPy array, 2 for the images and mask, and 2 for the validation data. Let's continue. Let's define the dimension of our input images. And now this is the important part. We are going to load from step number 2, build Res-UNet model. We are going to import our function that we name it build_Res-UNet. It's very important. And we are also, of course, importing a TensorFlow and some Keras function that I will explain later. The shape of the images would be 128 by 3 channels, which means this is a color image. The learning rate would be 0.001, and we are going to define a batch size of 8 images, and we will run 50 epochs. So let's load our model and print the summary just to double check that everything is okay. As you can see, we have some errors. Max pooling. I think the problem is uppercase, so let's fix it. Good. Let's run it again. We have another error. I think it's another problem of uppercase and lowercase. Yes, it should be a lowercase. So let's fix it and let's run it again. And now it's okay. As you can see, we have a summary of our model. Okay, so let's continue to the next step. Next, let's define our optimizer. Of course, it will be based on Adam, and as argument we are going to send the LR variable. Now we are going to compile our model. Since it's a binary classification of 0 and 1, so we'll define it as binary cosentropy and send our optimizer, and the metrics would be of accuracy. Then let's define the steps per epochs for our model. The steps of epochs is the number of train images divided by the bit size, and let's round it using the ceil function. Validation step is very similar, but instead of train images we are going to change it to the number of validation images. Now let's create a file name for our model. We will name it melanoma Res-UNet.h5. A very straightforward process, same as my previous tutorial. Next, let's create the callbacks. So the callbacks is we set the callbacks for model checkpoints. For saving the model, we can reduce the learning rate on plateau, and we can of course do an early stopping if our model doesn't improve after several steps. For example, as you can see, model checkpoint save the model if it was improved. The reduced plateau changed the learning rate during the training, and the early stopping would stop the training if there was no improvement after 20 epochs. May I remind you, we are running it for 50 epochs. And at last, this is the training process, which is based on the Feit function. We are sending several arguments. As you can see, we are sending all the training images, all the training mask, our bit size. Each bit size has 8 images. Also the number of epochs, which would be 50. Our validation data, which is composed of our validation images and validation masks. Also the number of validation steps, the number of steps per epoch, and anything else? Yes, we are going to shuffle all the data, and our defined callbacks. And I think we can run it. Okay, let's run the function. As you can see, the training starts 1 out of 50. So this training process is about 3 hours, so I'm not going to wait all that time, and we are going to jump directly to the last epoch. Let's wait a few more seconds. I will stop the video here and start from the last epoch. So the last phase will be testing our model. As you can see, the model stops after 21 epochs. We have the value accuracy is about 0.72. I can see 7.73 as well. So basically this is the validation accuracy, and we can see we saved the model as melanoma Res-UNet.h5. So now let's choose one of the test images. Let's take this image, and we will try to predict the black area of this new test image. This image was our model never saw this image, so we will try to predict and create a mask of this melanoma. So now we are creating a new Python file. We will import a NumPy of course, and a TensorFlow. And the first phase would be load our trained Res-UNet model using the load underscore model function. So let's copy the name of the file name of our saved model, and let's load it. In order to see that our model was loaded correctly, we will once again print its summary. As you can see, we have a summary of the model, so it was loaded correctly. Now let's define the relevant parameters. The dimension would be 128 by 128. And now let's load a test image and show this image. And of course we will use this image and pre-process it for our model. So let's copy the full path. And let's show this image using the CV2ImShow function. We will name this window original image. Of course, it's a color image. So we are expecting to see the image on the screen. As you can see, the dimension of the image is very big. So let's reduce it. So let's say you reduce it to a scale of 25%. So we will create a width and height for this specific image view. First of all, let's create the dimension, the width and the height. We are extracting the shape of our original image, and then we are creating a new variable. And we will use the CV2 resize function in order to resize it to 25% from the original image. This reduction is relevant only for the presentation of the image. It's not relevant for our model, since in our model we used a very strict width and height. So let's run it again. As you can see, now we can see our original image. So let's continue. Now we are preparing our image for the model. So this preparation process is divided for several steps. First, we are going to resize to our width and height, 128 by 128. Next, we are going to divide the pixel by 255, so it will be between 0 and 1. And then we are going to use the expand dims function in order to add another dimension, since it's a batch of images. So we are creating a batch of one image inside it. Our model expecting a batch of 8 images, so we are creating a batch with one image. Then we are running the prediction, and then let's print the shape of the results. We are expecting to see a shape that is basically and black and white image. As you can see, 100 by 128 by 128 by 1. So it has a values between 0 and 1. So what we are going to do, so this is our predicted mask. We are going to change the value. Since it's a binary prediction, all the values between 0.5 we are going to replace it to 0. So we will see black. And all the values above 0.5 we are going to replace to 255, so it will be presented as white, and this will be our melanoma section. So this is the code for this process, and now this result mask is our predicted mask for the melanoma. In order to show it, let's change it to our the same dimension for our original image, so we can put one next to the other. So now we are ready to display the image. The name of the window will be predicted mask, and we are going to display the mask. So I have one error. Let's fix it. Yes, the name of the function. Let's run it again. As you can see on the left side, this is the original image and this is the predicted image, and we predicted 2 areas. Cool. So now let's add another image, which is the ground truth. That means we will take from our dataset the real mask of this test image, and we will display these three images one next to each other. So let's copy the full path of the ground truth mask and then display it. We'll adjust the dimension as the same for the previous one, and we will show the three images together. We will call this image true mask. We are loading the image using the same functions of imRead, and of course it's a color image, but not really important if it's a color or a black and white. We are resizing it and displaying it. And let's run it. As you can see, we have three images: the true mask, the original image, and the predicted. I hope you enjoyed this tutorial. I really appreciate if you subscribe my channel. More tutorials will be uploaded in the next weeks. Bye bye.